Welcome to The Explainer. Today, we're going to play detective and crack the case of one of the most fundamental principles in all of electronics. It's called Kirchhoff's voltage law, and it's basically the secret weapon engineers use to figure out exactly what's going on inside any circuit. All right, let's dive right in. So imagine you're staring at a map of a circuit, kind of like this one. You can see all the parts, you can see the path the electricity takes, but key pieces of info are missing. How can you possibly figure out the hidden voltages across these components? I mean, it really does look like a puzzle, right? But believe me, there's a super elegant way to solve it.
Visit youtube.com/avidsystem and don't forget to subscribe.
And for that solution, we have to go back to the 19th century and thank this guy, Gustav Kirchhoff. Now, he didn't just give us a little hint. Oh no. He gave us the master key to unlock these kinds of electrical mysteries, a rule that works for every single circuit, every single time, no exceptions. And that key is what we call Kirchhoff's voltage law, or KVL for short. And you know what? At its heart, the idea is actually really simple. It just says that if you take any complete round trip, any closed loop through a circuit, all the voltage changes you see along the way, they have to add up to exactly zero. Period. So here's the crucial point. Think about it. As electricity travels around in a full circle, right? The energy it gains from something like a battery has to be perfectly, and I mean perfectly balanced by the energy it loses in things like resistors. You see? No energy just appears or vanishes. It all has to even out in the end. Now, what's really fascinating about this is that KDL isn't just some random rule somebody made up for electronics. Not at all. It's a direct result of one of the most fundamental laws in all of physics, the law of conservation of energy. It just reinforces that basic idea that, you can't get something from nothing. Okay, to make this super intuitive, let's think about a roller coaster. Just picture it. Imagine that voltage is like the height of the roller coaster track. You get cranked up that first big hill, you race down through all the drops and the loops and the turns. But when the ride is finally over, where do you end up? Right back at the same platform you started from. Your total change in height is zero. In this analogy, it perfectly captures the two sides of KVL. You've got your voltage rise, that's like the lift hill on the coaster, the part that gives you all that potential energy. That's your battery. Then you have the voltage drop. That's the thrilling plunge down where all that energy gets used up. That's your resistor, doing work like lighting up a bulb. All right, so let's put this into practice and see how this law becomes a real tool. We're going to use it to solve our very first case, a nice, simple, single-loop circuit. So here it is. We've got a battery, we know its voltage, and we have two resistors, we know their values. The big mystery we have to solve is, what is the current? What's the actual flow of electricity running through this loop? KVL is going to be our guide to find the answer. Okay, to crack this case, we're going to follow a really clear 5-step method. First up, we just assume a direction for the current. And hey, it doesn't even matter if we're right. The math will actually fix it for us later if we guess wrong. Second, we'll mark the polarity, the plus and minus sides across each resistor. Then, third and fourth, we'll trace a path around the loop and write out our KVL equation. And finally, the fun part, we solve it and find our unknown current. So if we follow those steps, our KVL equation ends up looking just like this. We've got the voltage rise from the battery, and then we subtract the two voltage drops from our resistors. And as the law tells us, all of that together has to equal zero. But wait a second. Our equation still has unknown voltages in it, right? The drops? So to solve this, we need to call in KVL's famous partner, Ohm's law. You've probably heard of it. Voltage equals current times resistance, or V equals IR. This amazing tool lets us rewrite those unknown voltage drops using the one thing we're actually looking for, that current, I. And from here, it's just a simple bit of algebra. All we have to do is rearrange the equation to get that I all by itself, and we can calculate its exact value. And just like that, mystery solved. We now know the precise current flowing through that circuit, all because the law gave us the perfect framework to figure it out. Okay, so that was the warm-up round. Now it's time for the main event. Let's really put KVL to the test and see how it handles something a bit more complex, because this is where you see its true power. So, what happens when you have a circuit that isn't just one simple loop, but a whole messy network of them? I know, it can look pretty intimidating, but the absolute beauty of KVL is that the fundamental rule doesn't change one bit. The exact same law applies to every single individual loop you can find inside that complicated network. The method is exactly the same, it's just scaled up. You just identify each loop, one by one, and you write a KVL equation for each of them. What you end up with is a system of equations, and when you solve them all together, bam! You can find every single unknown current and voltage in the whole network. It is an incredibly powerful technique. So, we've seen the law in action. It's pretty cool. But let's zoom out for a second. Why does this one rule, something from way back in the 19th century, still matters so much in our high-tech world today? Well, for starters, KVL is also known as Kirchhoff's second law. And when you pair it with his first law, which is all about current, the two of them form one of the absolute cornerstones of all circuit analysis. We're not talking about a helpful trick here. We're talking about something truly foundational to electrical engineering. So let's break down the key takeaways. First, KVL is all about the conservation of energy. It's a fundamental law of physics in action. Second, it's a simple promise. The sum of all the voltages, the rises and the drops, in any closed loop has to be zero. And because of that, it gives us a systematic, basically foolproof way to analyze and troubleshoot any circuit, no matter how simple or complex. And the impact of this law? Oh, it is absolutely everywhere. Think about the smartphone in your pocket, the power system in an electric car, even the massive global power grid. Every single time an engineer designs any of those things, they are relying on Kirchhoff's voltage law. Let me be clear, without this principle, our modern electronic world just wouldn't be possible. Which of course leaves us with one last question. We've totally mastered KVL, the law that governs voltage as it goes around a loop. But what about the current? What happens when it gets to a junction and has to split up? Well, it turns out Gustav Kirchhoff had a law for that too, and well, that's another mystery for another day.
Thanks for watching.